let's resume the workshop. And it is my pleasure to introduce the next speaker, Victor Araman. Hi, Victor. Victor received his PhD in 2003 at Stanford University, and recently actually became a professor of decision science at the American University of Beirut. His research interests are on stochastic modeling and control, with focus on queuing, dynamic pricing, and machine learning problems. He serves on several editorial boards like AMSOM, NRL, and queuing systems. And today he will be, as his slides already show, schedule traffic with applications to queues. Please, the floor is yours.
So hello, everyone, and thank you, Fiona, for the introduction. It's actually a great opportunity to be talking in this workshop. I enjoyed the talks, and I will be talking about service management as well in one way or the other. This talk is a joint work with a few people, in particular Peter Glynn from Stanford, but also Hong Chen and Ling Chia, and it's a work that we have been working on and off, in particular with Peter, related to this topic of scheduled traffic. And I thought it would be interesting to kind of put some of our results together, and share them with you. There is a part of these are published work, recent or a little bit earlier, and some are actually ongoing that we're basically trying to finish. So also comments and feedback at the end will be mostly welcomed. All right, so in some sense, we started on this work by wondering really like many years ago about the assumption of renewal processes as typical input traffic for queuing, and there were some work about non-renewal to some extent, and we try to put our thoughts together to build a model that is to some extent theoretical, but tells us a little bit about another type of process that could be interesting in the case of service management in general or in queuing. So really my objective here is to discuss a non-standard class of input traffic, basically driven by appointment-based systems. So in some sense, it's in the same context as Marco's previous presentation, and actually previous work of Harsha as well. So to some extent, there's a common interest here among three of us. But also, the applications, I think, is beyond also an appointment-based system. What I would like to do is to share with you some, results that I think are interesting and, make us think about, queues maybe in a slightly different way, and give some hints or intuition on some of, of why this is happening. Really, the main kind of conclusion or objective to some extent at a high level is to validate how effective and robust scheduling systems are, despite the presence of uncertainty in such a system. So I'm starting like really on very broad range of application of queuing. Since Erlang, we know that queuing has been playing an important role in modeling basically systems. But what I like in this is that technology has been advancing, our way of living has been advancing, and models of queuing has been adapting to also our new needs and new issues and so on. And I want to highlight in particular, these two applications. The other one we're probably all very familiar with them, these as well, but kind of from a queuing point of view, I think that's interesting. So there's the telecom literature, there's the call center that really made a huge impact on, pushing people to do even more research that is also applied and effective. Many models related to, distribution and manufacturing also take queuing into account. And then there are the typical queues that are out there. But on those two examples are basically, more or less recent, this notion of double-sided platform. For example, the Uber, we're all familiar with that one, probably less familiar with this. Basically, on the Uber end, you have two streams of, some stance, players or agent and a platform in the middle, right? And, customers will be waiting until, a driver comes, and a driver will be waiting until there are allocated requests, right? So there is this kind of double-sided part that I think is interesting, and there is recent work. I'm also working on such application beyond that discussion of today. And also there's plenty of platforms today that are in this so-called gig economy trying to match, let's say, workers with tasks that they need to do, right? So Uber would be a specific example of that, but the number of applications related to kind of crowdsourcing is growing, and queuing is this kind of double-sided queuing is an important, I think, application of queuing theory. Sorry. All right, so basically we have a structure. A queuing system is driven by a discipline that we need to set. So, for example, in the case of Uber, we want probably the closest driver to the request. We have a certain number of stations in parallel. We have a queue size, so that's a structure that is designed. We basically have information about the system. So typically we have jobs that are need to be processed, and we have arrivals to the system, right? These are the primitives of the problem. So data-driven estimation, parametric models. For the job processing time, it's typically some kind of ID sequence, could be stationary. Where I think the main primitive that is very sensitive to the result and to the application is the input traffic, right? The type of traffic that actually comes into the queuing system is really, the most representative of the application and the setup we're in. So I'll come back to that in a second. And then we have some output measures related to the workload, to the queue size, to the waiting time, as we know. Right? So on the input traffic, as I started by saying, typically, the most famous, renowned, you name it, input traffic is that Poisson process. And in many ways, it's quite powerful, standard, simple, yet quite powerful. In particular, in my mind, is the superposition theorem that makes it extremely actually relevant in application and validated in some application with data and so on. A renewal process, more general class. If we think about it, kind of less applicable than a Poisson, yet it can be used and fitted in data. Class of input process that also had an impact in so many different applications is Markov modulated processes, in particular, for example, a Markov modulated Poisson. But again, there's this, this notion of multiplexing ideas that actually also made it quite powerful and useful in practice. People looked at non-stationary setting, particular maybe a non-stationary Poisson process would be a typical, input traffic that allowed some kind of tractability in the literature. All of these have a fundamental characteristic, as you probably have guessed, is that there is this kind of, sequence of inter-arrivals that are there, right? Driving that basically there's this clock that starts once an arrival arrives and then, defines when the next one will be arriving, right? And, to simplify things, this is approximated by some kind of Brownian motion in a heavy traffic setting. And the Poisson process is, the counting process is kind of defined by, all the uncertainty that was in the system up to time t, right? Some kind of hitting time hiding there, right? Now, another dimension of input traffic is those, driven also by a lot of data-driven result on internet traffic and similar processes with, different types of stochastic processes, let's say fractional Brownian motion with Hurst parameter larger than 1/2, talking about the burstiness of the traffic and accounting for the positive autocorrelation that is embedded in this traffic. Having said this, what about those settings? Right, and in some sense, as I said, this is in the spirit of the previous talk, whereby we give appointments. The appointments-based systems are there, and a major part of our to some extent daily system. And let's say queuing systems in books don't consider, this input traffic, except if we assume it to be a deterministic, maybe input, some kind of, some kind of DDS to some extent. Either we have, a queue that is going to infinity, or, basically with utilization larger than 1. So you basically, the buffer start increasing at a, linear rate, or otherwise, we can control and, start decreasing at another linear rate because, rho becomes lower than 1. So what are these settings? Again, appointments to clinics. We give an appointment, and people arrive. They might arrive early, they might arrive late. So there is still an uncertainty that typically we dismiss. Arrival of planes that are scheduled to arrive on a terminal is the same thing. A flight can be sometimes, a day and a half late, right? Or hopefully just 10 or 15 minutes early or late. We talked about distribution system. A lot of the distributors basically put orders every week, or every day, right, on a particular day. So basically there's some kind of time at which the order went, and then they receive it a lead time later, right? And this lead time could be, coming up in a sense, allowing for orders that are, put earlier to come later, and vice versa as well. With Fresh Direct, this is on individual level. We go to our, this is a major online grocery store on the East Coast, where you put in a slot the time you want, and then they will deliver based on some kind of this schedule. The Amazon Flex example is an interesting one. It's just to inspire more than really trying to model it here. But basically the last mile delivery, I will come back to that, but the last mile delivery is outsourced to some drivers who actually suggest the time where they will be working during a slot of time will be, coming into work. They can come late or early. And I will also mention a cash flow example that is also, I think, quite natural, that is linked to this notion of scheduled traffic that I will be defining next. So what is a scheduled traffic? Basically, is a schedule that is given, right? With let's say every 30 minutes in a doctor's clinic, we have a schedule, an appointment, right? And so basically customer number N will be basically scheduled to arrive at time N times 30 minutes, right? However, this customer, this patient will arrive either early or late. So this is very much linked to this particular patient. There's a perturbation around the time that was scheduled, or initial one. And this perturbation could be stationary in the stock. I will just assume it to be IID. And so the arrival really happens at time NH plus psi N. And that's what I'm going to be calling the scheduled traffic. Now, interestingly, this is not a new process. It's actually, we believe the first time we were able to find a paper on that topic is by Winston in 1959 that actually discuss bounded perturbations joining or feeding a queue with exponential service times. I'll come back to literature review, but go through it quickly later. But I thought I would just say here that we're not creating this. This already have existed for more than half a century. Now, how do we write this counting process? Basically, it's a sum of indicators that you would expect of those arrival times happening in the interval 0t. Already, we can see a major difference with the renewal process, whereby the uncertainty, the entire uncertainty has to be considered in order to define how many people will be arriving in 0t, right? Because you might have early arrivals that are in the most general case that were expected to come much later on, and are coming now, and some arrivals that were supposed to be coming around this period and actually will end up coming much later. For the rest, I will assume H equal to 1, but this is obviously without any loss of generality. So I want to just focus a little bit on two examples that I think is interesting. And my objective is not to solve them here, rather to kind of like say that, these are interesting problems out there. I'm working in a different work on something similar, but that induce actually a better understanding of scheduled traffic. So back to this kind of Amazon Flex one, think of a retailer that is receiving orders from end customers, like a Poisson process of orders, right? However, the last mile delivery is actually outsourced to some flexible workers. What do I mean by flexible workers? These are not employers, but basically like Uber-like, let's say, driver. So we might think that actually a system to manage that would be some kind of Q of T. And Q of T is the number of drivers or workers available at time T. All right? Now, the number of workers available is basically the ones that that are expected to come by time T, that are in the system, by time T, minus those that actually, those that left the system by time T, minus those that, that came in by time T. So N of T minus T is the number of drivers that are available at this point. Remember, H equal to 1, so, my appointments are by T. I'm using this example because indeed in the case of Amazon Flex, workers will basically pre-select the time when they will be working, right? And then you can expect that then they will work for a random amount of time and they leave, right? We could also add maybe an uncertainty on the time when they arrive as well, right? They're not so much penalized per se by coming in late to the time they committed to come, okay? But all this is kind of defining this kind of, time where I'm supposed to be starting, and then, when I leave is, a random amount of time later. And my random amount of time is independent of other people. There's no queuing here happening between drivers, right? And so now an interesting question is, what would be the performance of this Q of T? And clearly for that, you want to understand Q of T and it's basically how does it behave and so on, all right? So in here, we'll be talking about Q of T rather than, this of Q of T, but you got the point. Another example is this cash flow that I mentioned earlier. That's another service business. Think of a credit card service that actually receive payments from customers, right? But then customers have some defined time, let's say at the beginning of a month or second day of the month where I need to make my payment. Now, those payments come in either early or late. So somehow the payments that you're making are driven by scheduled traffic. And the payment you make is, let's say, following some IID, random variable. And so the total amount of revenue or income of cash that the credit card is receiving is this sum up to N of T of theta J. But then this company has to be using this pool of money to pay its own, let's say, cost. So there is a cost payment, let's say, constant at a rate of, C. It could be salaries and other defined cost. And so we could be interested in some kind of ruin probability that is now driven by this scheduled traffic. All right, so back to this scheduled traffic, what's the primary interest here is really try to, understand, the impact of that traffic on a single server queue, in particular, an SD1 queue. Okay. First, let me just highlight the fact that if the perturbation is positive, then N of T is nothing else than the departure process from a DG infinity, right? People arrive at time N, spend the psi N in the server, and then leave. So the system is not really purely deterministic, nor a renewal-like. We're going to use the notation S for that. For this SD1, which I'm going to compare to a DD1 and GD1, basically we're going to approach it by doing a happy traffic analysis and try to understand how the result differentiate from standard result on GD1. Going to look at stability of the queue, where you will see that there is some interesting behavior there in scheduled traffic. And also tail asymptotics. I'll talk a little bit less on tail asymptotics of the workload, but on other tail asymptotics here. But in other work, we discussed the tail asymptotics of the workload of that SD1 queue. That's why I put it in gray. All right, now, why the emphasis on SD1? First, because since actually, early 60s that were proven that an SD1 from a heavy traffic point of view will behave like an SG1. That the SG1 will behave like a GG1, like a DG1. So an SG1 will behave like a DG1. And the uncertainty of the service time is large enough to actually, kind of kill the uncertainty at the scheduled traffic. And so on a heavy traffic basis, when looking at that scale, then in fact, the perturbation will play no role. And so in order to understand the impact of the scheduled traffic, then we really want to kind of like reduce that uncertainty to D to really highlight that and compare it to a G1. That's number one, but also because, SD1 have, their own interest, right, where processing times are almost deterministic, are by itself an interesting queue to actually analyze. So quickly on the literature review, like I said, there's some papers that are, historically looked at specifically scheduled traffic. In particular, Kingman, as I said, looked at a heavy traffic result in general for single server queue that would actually apply to scheduled traffic with a general distribution for the processing time. The others are basically some characterization of the waiting time, but that's really not really amenable to analysis as we're trying to do here. More recently, so this paper in 97 that actually looked at the aircraft arrivals actually of planes, looked at bounded perturbation and show that a single server queue with driven or fed by scheduled traffic and bounded perturbation is actually can be stable even if rho equal to 1. Right? So that was actually quite an interesting result, that if the perturbation are bounded and the processing time are deterministic, then in fact rho equal to 1 is a stable queue. We have some work, and we'll be discussing some of that on this. Otherwise, the related literature really is about appointments based or processes, for example, here that look at arrivals with no show, or for example, an assumption whereby if your arrival is delayed more than the next schedule, then you're assumed to be dropped out. So in other words, this work kind of guarantee some kind of first come first serve property, in a sense that you don't cross over the next patient or the next customer, right? You could not show up, or if you're late, then you're actually bounded by the arrival of the next person. And there's also a number of papers related to appointment-based, either trying to obtain, a optimized appointment, like again Marco's earlier work and some other work in the literature, or trying to, for example, model. And I think yesterday's one of the talks was about basically defining a appointments or rescheduling appointments based on how the system is changing. For example, in this paper, they look at an appointment that is driven by a queue, and then as a result of those appointments that are set, then basically some people will show up, some people will not show up. However, in the clinic, the arrival among those that will show up is renewal based, right? So it's not driven by a scheduled traffic. Probably the closest work is to philosophically, but also in one of the application of this work is on scheduled traffic. So transitory queues is the basically set of queues where they have a finite population, and every customer or patient has a clock, and then when their clock basically comes to an end, then basically they arrive, right? So you have somehow the sequence of arrival is driven by some statistical ordering, and that will determine kind of the arrival to the single server queue. Now, Harsha also has paper with Amy where they look at, in one example, on scheduled traffic, again in a finite population, trends in time, where their perturbation is to some extent bounded, and then they obtain some diffusion approximation by letting the number of the population or the number of arrivals grow large. Let me start with a simple case. Suppose the perturbation is exponential. What can we do? We can actually have an exact analysis, right? We actually, if we define, so here we're looking at people that just are late, where nobody comes early. And we define the number of people that are late at time n. And so this actually quantity is easily shown to be a positive recurrent Markov chain. I'm not going to do that, but basically it's not hard to show by taking advantage of the property of the exponential that in fact that's a Markov chain which we can completely define its transition matrix. Right? We can show that it's positive recurrent again, and then have a full characterization of all the moments of that quantity. And we can also show that the stationary distribution of that, the tail distribution of that late arrival is actually lighter than exponential. It's actually can be, it's p is e to the minus alpha. So this is kind of lighter than an exponential distribution. And as opposed to the previous work that I mentioned, where the perturbation bounded leads to a single server queue that is stable when rho equal 1, here we can easily show that in fact, the workload process is gonna actually converge to infinity almost surely. Right? So in this case, the queue will be unstable. And so it seems like the boundedness of the perturbation is a strong or a hard constraint for that stability, but I'm leaving question mark because the last slide will be saying maybe something slightly different. All right. So some properties that I think are interesting, some are cute, but worth sharing. So if we look at n of t, with no assumption whatsoever, except that the xi's are in this case IID, there is always a time stationary version of n. Right? And how do we obtain that? We actually by randomizing the starting point at 0 by some uniform distribution, by some point uniformly distributed between 0 and 1. Right? So basically we're adding this u that is independent of the perturbation, and n of t is shown to be a time stationary process version of basically the scheduled traffic with a link to a particular perturbation sequence. We can show that the expected value of n of t is equal to t. This is the stationary. From now on, I'll mainly focus on the stationary version. Otherwise, I will make it clear. And this is true whether the perturbation has finite mean or infinite mean. In that same mindset, n of t has a light tail, whether their perturbation has a light tail or heavy tail. As a matter of fact, the right-hand side here is the tail related to a Poisson process. The covariance of the increments is negative. That's also not hard to prove. But what I think is interesting here is the intuition is that indeed this is really about schedule, means that if more people show up earlier, then you expect less people to show up later. Right? And that is, always the case that the covariance of those increments is negative. Now, we define these two processes, late arrivals and early arrivals. Basically, late arrivals is basically this quantity that is defined by all those that didn't show up by time t and they were supposed to come by time t. And earlier, those that were not supposed to arrive by time t and actually, arrived by time t. These two quantities, it's also a simple application of Borel-Cantelli lemma, shows us that these quantities are finite valued if and only if the positive respectively the expected value of the positive value of psi is actually finite, or the negative So the minimum between minus psi 0 and 0 is finite for the early one. So basically, some kind of finiteness of the perturbation is needed for these quantities to be finite, and that's an if and only if. But it's interesting to remind you that I just told you earlier that n is stationary no matter whether the perturbation actually has a finite mean, right? So the perturbation, the stationary version exists even though the late, quantity or the early quantity is not defined. That could be the case. So something is happening between finite mean and infinite mean that we're going to a little bit analyze as well. This is the first result that is really an observation. This is actually an interesting one, but nothing major, that tells us that actually the number of arrivals that happened between 0 and t minus those that were expected or scheduled is equal to those that came early minus those that came late. So extremely intuitive. This first term is independent of the perturbation. It has really to do only with the fact that we introduced this uniform random variable to make the process a stationary one. So it's a number between basically minus 1 and 1. As a result of this, we're able to actually prove a strong result that shows that n of t minus t is a stochastically bounded random quantity. Meaning that, if I let this specifically what we mean by this mathematically, of course, if we divide this n of t minus t by square root of t, this is converging to 0. So it's really a much weaker behavior than a renewal process that is behaving as in square root of t as a result of a central limit theorem like result. What the theorem is saying is basically if you fix some s between 0 and 1, then n of t with respect to that s, so t is n plus s, minus t is converging weakly to a random variable that is independent of n and only depend on s. Right? So there is, this strong result that shows us that n of t minus t is almost a bounded quantity. And we move, and for this we need the finite mean perturbation, right? So just to be clear, here we need the finite mean. Now, with that finite mean, we can actually get more about the covariance than just that its sign is negative. In fact, if we look at, for example, Pareto-tail-like perturbation, then we can get the tail of that covariance that also behave Pareto-tail-like. And that really tells us that the conditional autocorrelation is always summable. We also obtain the tail for that quantity when the perturbation has an exponential tail as well. And the covariance behave almost the same when things are symmetric, then in fact Cn is in capital O of n. Now, just remember Cn is a negative quantity. All right, so we can really determine the covariance of the scheduled traffic with respect to the increments. What about tail asymptotics? It's probably one of our main results, that the tail of n of t, if the perturbation is quite heavy-tailed, yet with finite mean, then in fact n of t behaves like a Poisson-like, the tail of it. For lighter tail, it has lighter tail perturbation. And the result is based on a general result about infinite sum that we obtain that could have other application beyond what we're doing here. So let me state the result. This is our result. We're saying that the tail of the scheduled traffic is basically, has a Poisson-like in logarithmic term, but we also have a tail, exact tail asymptotics as well that I'm not showing here. And it's rely on this result. Think of a random variable defined by a sum of Bernoulli, where the probability of success of the Bernoulli is of this form Cn minus alpha. Okay, so you have an infinite sum of Bernoulli random variables where the probability of success of the Bernoulli is basically asymptotic to Cn minus alpha. Then we show that the tail of that quantity is, given by, has some kind of large deviation feeling, but it's not exactly large deviation, right? Because this is a random variable here. Right? And however, the proof is inspired by larger deviation, result. Not gonna go through it with given the time remaining, but basically we, introduce can get easily an upper bound, for example, using some Markov inequality and looking at the log moment generating function, simply gets that kind of upper bound. With the lower bound is much trickier to get it, but you can already get a feeling that what's really the rate of convergence that one gets out of that approach. So you need to work harder there. For the lower bound is actually follows a little bit the proof as well of the exact tail asymptotics. So for example, that same quantity that I defined earlier, we can actually get exact asymptotics for it. Right? That is, quite complex and based on change of measure ideas, kind of as expected from what I said. So in other words, also inspired by large deviations. What I like in the proof and I would like to highlight is that basically, you do your typical change of measure. Of course, you need to pick here and be careful on how you're picking, the theta that you want to use. But then a nice application of the local central limit theorem gives us the result. Really, these are the main steps, and we're able to show that the expected value of that quantity z is almost linear in n, and the variance of that is also linear, and we take advantage of this through that central limit theorem. All right, so what are the results out of this? We basically now we leverage on those infinite sum of Bernoullis to actually show that the workload, if rho equal to 1, and the perturbation has a Pareto-tail, is in fact growing very slowly, but to infinity. Right? So it's an unstable. However, we're so far away from the square root of t given by a typical GD1Q. Right? But clearly, we're in an unstable setting, for example, compared to a DT1. And one interesting, basically, observation here is that by writing the workload, we actually able to manipulate this and show that the workload is equal to the maximum of an early quantity minus a late quantity, like I defined earlier, but of the time reversed system. And so, by having, by being able to control on these quantities, we're able to control on W of t. And so that's the results that I was summarizing earlier, right? So what happens with under heavy traffic? Again, we're basically showing that, the workload is gonna go to infinity. However, the scale is very different than a GD1Q. The W basically here reach equilibrium much faster than a GD1, right? In 1/1 minus rho in terms of time scale, while for a GD1, the time scale is basically 1/1 minus rho squared. So here we reach the equilibrium scale, the equilibrium much faster. Notice this assumption here. Again, what we're expecting here, this is interesting, I think, point. We're only putting a constraint on the mean of the perturbation with respect to its left tail, nothing more. However, we're requiring the perturbation on the positive positive tail to have a Pareto. Right? So, and if I go back as well to the previous slide as well, I should mention here that what is interesting in that actually quantity, which we use in the next result as well, is that there is a asymmetry between early and late quantity. Right? Basically the workload here is impacted more by those early rather than the late. And it's not clear, at least, to us first, of why this is happening, because, you have this kind of infinite points, right, that you're perturbing, right, the way you want, yet, somehow late arrivals have a bigger, impact on the workload than early arrivals. Now, if you want to look at a multi-server queue, for example, if I have in mind this Amazon Flex, then we will need another scaling for that, and everything I will mention is the scaling that one can use. So, for example, we can, increase the number of arrivals by scaling, by n. So basically, by making the inter-arrival, the schedules to be very small, to go to 0, we don't touch the perturbation. So the perturbation becomes very large with respect to those schedules, and we can show a functional central limit theorem there somehow a la Borovkov that is actually meeting the conditions that are needed, for example, to obtain a half-limit regime result like Josh Reed's work in 2009. So basically that input process that is, if we think of SG, N here, basically, that S is actually, meeting the condition for the result of multi-server queue under half-inwit regime to hold. That's all I would say about this. We didn't talk about infinite mean. This is an earlier work, but I think is interesting. In fact, if we allow the perturbation to have infinite mean, right, we go crazy with that. It's Pareto in this case. Then actually we show that the number of late arrivals is basically behaving like a fractional Brownian motion with a Hertz parameter less than 1/2. So what is interesting in this is that probably this is the first, kind of interpretable explanation of Hertz parameter less than 1/2 in a queuing context. Right? That is actually, of course, confirming this negative correlation between the increments. Now, if we let alpha goes to 0, so we're really perturbing for crazy those perturbations, then in fact, we go back to a Brownian motion. To some extent, there's some kind of noise that, kind of like appears again. Again, here the results are confirming the fact that scheduled traffics are much lighter than a renewal like. For example, the work, even though the perturbation has infinite mean, and again the magnitude of the workload is smaller, and the time scale are in the order of 1/1 minus rho to the power 2 1/2 divided by 1 plus alpha. So if you think of alpha close to 1, right, this is really 1 minus rho to the power minus 1, right, as opposed to 1 minus rho to the power minus 2 in a renewal setting. And the tail of that WT is in fact a super exponential. And so we're really far away from the fractional Brownian motion like input traffic with sub-exponential like tail. And this is the result that goes with it. Again, the proof is typically just showing that the finite dimensional distribution converged to the right Gaussian sequence, and then showing tightness of that convergence. So ongoing work, we basically tackled the question of stability. And we're trying to say, can we prove some if and only if conditions for the stability of a SD1? And our claim, and basically, this is what our observation now. We know that if the perturbation is bounded, then an SD1 is stable with rho equal to 1. We know that if the perturbation is not bounded, in particular, for example, if you take an exponential, then the SD1 is not stable. And our claim is that if the right tail is bounded, but no assumption on the left tail, then the SD1 will be stable. Which is, I think, an interesting result. Again, we're still, in the process of gaining, intuition about it and, working on it. But I thought it would be interesting to share it, with being careful that this is still, working. So I want to conclude. Queuing systems continue to play a unique role in modeling service systems, no doubt about that. Often the input traffic is taken to be renewal-like processes, and clearly, a huge literature on that, and that's very good. However, there are a lot of applications where it really doesn't make sense to consider a renewal-like process. One examples are this kind of appointment-based systems, but I gave a couple of examples beyond appointment that are very much driving this scheduled traffic to play an important role in governing the input traffic of that queue. We show that under finite-mean perturbation, NT minus T is a stochastically bounded random variable, so it's a very strong result. We have, believe, some conditions on the stability of the queue when rho equal to 1. When the stability of conditions don't hold, then WT exhibits much smaller fluctuation than in renewal-like systems, despite the fact that we took, a deep, the service time to be deterministic. We also obtain logarithmic and tail asymptotic for N of T. It's Poisson-like tail when the perturbation is quite heavy. However, it's lighter than that when the perturbation is light. Under infinite mean perturbation, we obtain a functional central limit theorem for the workload that actually involves a fractional Brownian motion with a Hertz parameter less than 1/2, and kind of expected given this negative correlation among the increments. However, we believe there are many interesting avenues to develop, basically with respect to multiple servers, driven by more specific applications. Again, application were inspiring the work rather than, we didn't take one application and we tried to solve it. Right? And I'll stop here. Thank you very much.